then what I like to do then is kind of continue on with some of the stuff that we were talking about today in lecture, a little bit more on some alcohols. Obviously, we'll talk more about it on Wednesday, but why we got some time here. Um, so obviously, we started talking about alcohols today. We also talked again about those reactions with alkenes and a couple of things about reactions when you are dealing with trying to write the formula of the product in these different sort of organic reactions. And by the way, there is, as I might have mentioned, so let me just mention again, that up on Canvas, there is sort of I want to say a worksheet, but sort of a paper that really describes all the different types of organic reactions that we're going to talk about, obviously, through these organic chapters, and some of which we've already sort of talked about. And again, what I try to do on that sort of sheet, if you look at it or have looked at it, or if you haven't, if you're going to look at it, again, I try to describe how the reaction takes place in sort of the simplest terms. And what I mean by that, and as I've been saying, as we've been doing some of these sort of drawing products and things of organic reactions, that, people always want to sort of make it harder than it should be. They always think, all kinds of crazy things should happen in these reactions. And really, hopefully you're starting to see a pattern in some of these ones that we're looking at that, as I mentioned, there's really only one part of the molecule that, really does change. Everything else pretty much stays exactly the same. And that's why I say, you pretty much have the product that you need to draw sort of in front of you. You just really need to copy it kind of basically piece for piece. And you just need to change that one sort of aspect of it. So earlier we were talking again about sort of those addition reactions, that are involving double bonds. And, again, it doesn't matter if, there's 400 carbons attached to this, just 2 carbons, or 3 carbons. Every single one of these sort of addition reactions, as we talked about, pretty much always works out the same. And it always is, when you see something like this, it is just this part that changes. And it's important to think about these reactions as, okay, what part of it changes? And it's really best not to think too much, actually, when you do these things, and literally just copy what's there. And like I said, you pretty much got everything there. And again, the thing that you need to remember is, okay, in this type of reaction, I started with a double bond. I know that thing should now become a single bond. And that, again, is really the only thing that should be replaced. And what that does now is, the other thing that you need to understand in these type of reactions is that this is an addition reaction, which means both of these guys will come on, and they will come on to basically one to each of the carbons. Now, we did talk about a rule about how they come on today, and we talked about it before, but again, that is what is referred to as the Macarthur rule. And basically what that means is the hydrogen in this unsymmetrical addition, again, will always end up at the carbon that started with the most hydrogens. So in our case here, again, on the right has the most hydrogens. That is the one that should get the hydrogen. The other guy should end up over there at the opposite carbon, and that'll get you your main product. Again, doesn't matter if it's a symmetrical addition where you're adding 2 of the same. In that case, you don't even have to worry about it. You simply make the double bond into a single bond and put 1 on each of the carbons. That also happens, obviously, with water, like we talked about. Again, we would follow the same rule for something like water. And again, this is what is referred to as a hydration reaction, because we are basically adding water. And same idea, we got pretty much the same setup. It's just going to be this part that's going to change. And again, I could have a ton of more carbons at the end of this thing. It doesn't matter. Always going to be the same, just single bonding it out, again, to make room for that addition. And same rule here, since we have a choice for our hydrogen, we're going to, again, put the hydrogen on the one that had, I'll just circle it, the more hydrogens to begin with. And then obviously the OH here on the guy that had the least number of hydrogens there. Obviously, we don't typically circle them. That leads us into what we were talking about today, which is alcohols. So in this case, a hydration reaction will result in basically the formation of an alcohol. So if you take an alkene like we did here, plus some water, you will get an alcohol. So we talked about naming these alcohols, and for example, this particular one here, this again has 3 carbons, so that's based off of propane. Because it's an alcohol, it then becomes propanol, OL. And the location of that OH group is at carbon number 2. This is what is known as 2-propanol. You sometimes will see this guy written like this. And this guy also has a common name that, if you remember what that group is right there, that is CH3CCH3. That is the isopropyl group. And that's why this is also sometimes referred to as isopropyl alcohol, also known as rubbing alcohol as well. So again, some of these guys do have some common names that's very commonly used, like isopropyl alcohol is used a lot, but it's also 2-propanol. Remember, 3 or more carbons with alcohols, you do need to give the number as to where the OH group is located. Also, basically, the OH group takes the priority in terms of numbering. So you would want to number the longest carbon chain, whichever way gives that OH group the smallest number, and then everybody else attached basically is numbered accordingly. Any questions on those things there? Now, we talked about sort of classifying alcohols. Again, we can classify our alcohols as primary, secondary, or tertiary alcohols. And again, it's kind of the same thing. Again, primary alcohol means that the carbon with the OH group is attached to one other carbon. Secondary means the carbon that has the OH group is attached to 2 other carbons directly. And tertiary means that the carbon with the OH group is attached to 3 carbons directly. So we can definitely classify these guys, based on primary, secondary, and tertiary. So for example, let's take a look at a couple here maybe. Okay, so why don't you take a moment or two here and decide what is the classification of each of these alcohols, and why don't you also take a moment or two here and give the name of each of these alcohols. Name and classification. Okay, so let's see how we're doing here. So we'll start first with the classification. So when you're classifying an alcohol, the important one is always the carbon that's attached to the OH group. And when we look at that carbon, we see that it is attached directly to 1 carbon there and 2 carbons there, which means that this guy should be a secondary alcohol because of that. Any questions on that there? Now, why don't we name it while we're here? So we got 1, 2, 3, 4 carbons in a row. 4 carbons is based off of butane. It obviously has the OH group. So that's going to be butanol, OL. Location of that OH group, again, we want to give it the smallest number. So going right to left will do that for us. It will give it a carbon number 2. And that would be 2-butanol. Again, if we went left to right, the OH group would be at carbon number 3, which would be a bigger number. Any questions on that one there? Looking at this one here, again, we're going to look at the carbon that has the OH group attached to it. And obviously directly attached to that guy is just one carbon. So that would be a primary alcohol because of that one carbon. That also would mean that there's only two carbons in this case. So that would be ethanol or ethyl alcohol, but ethanol is the proper name. No need to give the location because with only two carbons, this OH group is either at this carbon on the right, which would technically be carbon number one, or if you drew it on the carbon on the left, that technically would be carbon number one. So there is no real difference there. So again, the numbering really starts with about 3 or more carbons when you're dealing with alcohols in terms of that OH group. Coming down here, we're going to look at our carbon again that has the OH group attached to it. And in this particular case, it is directly attached to one carbon there, two carbons there, and three carbons there. That would mean that this guy would be a tertiary alcohol. The name of this guy, longest carbon group with the OH, 1, 2, 3, 4, 5, straight across basically. 5 carbons, again, is based off of pentane. Because it's an alcohol, it becomes pentanol. We want to give that OH group the smallest number, so that's a right to left move. So that's a 1, a 2, a 3, a 4, and a 5. That means that this is 2 pentanol. And we do have another group hanging out right there. That is a methyl group, also at carbon number 2. So that would be 2 methyl, 2 pentanol. Any questions on that name there? Lastly, here we're looking at a ring structure. That's a square, which basically means there is 4 carbons in that deal in a ring. That is going to be based off of cyclobutane. Because of the OH group, is going to become cyclobutanol. No need to give the location of the OH group. Again, it's assumed to be carbon number 1. Looking at this carbon, which is where the OH group is attached, it is attached to one carbon there and a second carbon there. And that means that this alcohol is a secondary alcohol. Any questions on any of those there? Classifications or names?
I do, Professor. Would you be able to explain how come on the ethanol we don't have to put the location of where the alcohol is located as far as like the CH3 or the CH2?
Yeah, so it's because really the reason we sort of give the location, for example, of the OH group or double bond or triple bond or any of those things is we really give the location when there's options for it to be in more than one place. So what I mean by that is if we look at ethanol, for example, like it is here in this particular example, the OH group is on, say, the carbon on the right, for example. And if we were to kind of go through the process of naming and also applying a number, which is not necessary in this case, if we did this guy, again, we would go with the 2 carbons, which means it's ethanol. And if we did give the location of this guy, we would number this guy carbon number 1, and this technically would be 1 ethanol if we included the number. The reason we don't need to include a number is because the other option you would have would be if you drew it like this, for example. And if you follow the same sort of naming procedures, we would do the same thing. This would be ethanol. And now because we always give the OH group the smaller number, we would actually number in this case left to right. And this would also then technically be 1 ethanol, even though it's on the other side. So even though it's on the other side, it's actually the same molecule. It's the exact same compound. And because there's really only one option for where that OH group is either going to be on the carbon on the left, which would be carbon 1, or the carbon on the right, which would be carbon 1. There's no need for the numbering in that. Now, when we get to 3 carbons, for example, and we put the OH here, this again would be 3 carbons, which would be based off of propane. This would be propanol. OH group here would be carbon number 1. This would be 1-propanol. Now, if we move that OH group to the second carbon, fill in everybody else. This again would be propanol, but we number 1, 2, and 3. This is now 2-propanol. This guy and this guy down here are 2 different compounds, and it does make a difference where that OH group is located. You actually get 2 different ones. Now you may be wondering, well, what happens if I kind of put the OH group over here? Well, if we put the OH group on the other side and we follow our normal sort of naming process here, this again would be propanol, and giving that group the smallest number, this would be carbon 1. We would number left to right in this case. This would be 1-propanol. This guy picture, even though it may look different to you, and this guy's picture even may look different to you, they're actually the same thing. They're exactly the same molecule, just been turned. So this is really not a new molecule. But we do get a new compound when that OH group ends up at the second carbon. We get 2-propanol versus 1-propanol. So it usually happens about 3 carbons or more with alcohols that you do have to give the number. Again, methanol, there's only 1 carbon, so it can only be in that spot. And ethanol, even though there's 2 carbons, it's ultimately the same compound, regardless if you put it on the left carbon or the right carbon. Naming wise, it ends up being the exact same thing. It's basically just the same guy, just turned around. Other questions on that?
Okay, thank you.
You're welcome. Other questions? Okay, so we talked about these classifications. We also started talking about some reactions there at the end. So let's talk a little bit more about some of those. We talked about hydration reaction at the beginning, where we take an alkene and we basically produce an alcohol. So when we produce an alcohol, it's basically that reaction, which is known as a hydration reaction, as we just talked about at the very beginning here, where we put on the water, again, as HOH. And as we talked about before, again, just going to break that double bond into a single bond and add in our H and OH. As we also talked about, the importance, right, is again that H in this reaction is going to go on the one that had the most H's to begin with, and this will get us our 2-propanol that we talked about before. Now, we can have a dehydration reaction that we also talked about a little bit earlier today. Hydration reaction is an addition reaction, which basically means we add both of these things. A dehydration is what is sometimes referred to as an elimination reaction, which means we're going to basically remove these 2 things. So when we start with an alcohol, let's say we started with this alcohol here. Let's draw everything out here so we can see all the hydrogens. And we'll go here. We'll do OH up top. And here. And this involves basically an acid as a catalyst, also heat, sometimes abbreviated with the little delta symbol. So in a dehydration, we're basically going to take away water. And water gets removed the exact same way that it gets added. So if you remember, we add water, OH goes to 1 carbon, H goes to the other carbon. So the 2 different carbons is how they get added. They actually get removed the same way. So the first thing that gets removed when we do a dehydration of an alcohol is definitely the OH. So that guy is coming off. That's basically this part of it. So we need to also lose a hydrogen. In this particular case, we actually have 2 options. Remember that the hydrogen doesn't go onto the same carbon, it goes to a carbon that's next to it. So in this case, we have a hydrogen on the carbon next to it. We could actually take any of these hydrogens if you like. But in this case, we also can take a hydrogen from the carbon to the left of it. And in this particular case, we have a choice. And the choice is basically opposite of how it goes on. So if you remember, how it goes on is the hydrogen goes to the most hydrogens on the carbon. When we remove it, we take the hydrogen from the carbon with the least number of hydrogens. So it's sort of opposite, which kind of makes sense. We put the hydrogen on the one with the most. When we take it off, we take it off from the one with the least. So sort of opposites of each other is essentially what happens in this reaction. So what does that mean? Well, we're going to look at this carbon, which obviously this is where our OH is going away. And now we need to look at the carbon to the left, and we see this guy has 2 hydrogens attached to it. We look to the carbon to the right, it has 3 hydrogens attached, which means the one that we're actually going to take is the one from the carbon with the least number of hydrogens, which means we're going to remove both of those things off. And you can see in the box, that is basically where our water comes from, our H2O in this dehydration. And again, we're going to take the H from the guy on the left with the least number of hydrogens originally, and we're going to take our OH from obviously the carbon that has the OH. Now you may be wondering, how do I draw what's left? And the same rule applies. Absolutely, positively, nothing else changes in this molecule except that we removed water. So what happens? We're going to redraw this thing exactly the same way. And again, I'm not going to really do very much other than just redraw it the same way. Obviously, I'm going to take the water out when I'm doing this. Now, what it tells me what happens is, if you just think about this reaction up here, we're basically going this way, which means what did we remove? We removed a double bond to put the water on, which means now when we take out the water, we put the double bond between those 2 carbons right there, giving everybody the correct number of bonds, and we go from an alcohol to an alkene in this case. Question on that reaction? Again, absolutely nothing has changed other than I took the water out of this empty spot and I replaced it with the double bond. So when we put water in, we have to remove the double bond to make room. When we remove the water, we put the double bond back. Double bond always goes between the 2 carbons that you took off the hydrogen and the OH from. Any questions on that dehydration reaction? If you did the opposite and kind of took the hydrogen from the guy to the right, that gives you the minor product, but this is the major product, and usually that's what you should try to draw. Now, some other important reactions that alcohols undergo are basically redox reactions, if you will, are oxidation and reduction reactions. So really an oxidation, as I mentioned earlier, several definitions: losing electrons, gaining oxygen as you go from reactants to products, losing hydrogen as you go from reactants to products here. Reduction is the opposite. It is gaining electrons, losing oxygen as you go from reactants to products, and gaining hydrogen as you go from reactants to products. So what happens in this type of reaction depends on really the alcohol that you're dealing with. So a primary alcohol as we talked about at the very end there, we'll go through a oxidation reaction. And the oxidation reaction we're talking about here in terms of our primary alcohol is this right here. So, excuse me. I'll do this guy here. Let's do this guy. We'll draw everything out so we can see what we're dealing with. Actually, let me draw it the other way so we can see it a little bit better. Doesn't really matter, but at least it'll be in the right orientation here. All right, we'll put our OH over here and our H and our H. So an oxidation reaction is sometimes abbreviated with this little bracket and O. And the definition we're going to talk about in terms of oxidation here in these reactions is this definition right here. We're talking about losing hydrogen as it goes from left to right. So in this case, when this alcohol goes through an oxidation reaction, by the way, again, this is a primary alcohol. We know that because when we look at this carbon, it's attached to one other carbon here on the left, so it's a primary. When we go through an oxidation with a primary alcohol, we lose H2. One H from the carbon and oxygen, basically. So on each of these things, they have an H. We lose one here and one here. And those two are the things that get lost. So if we look at this primary alcohol, and if we come up between the carbon and oxygen bond, that is the hydrogen that's attached to the oxygen. That is what's going to get lost. And you could choose either one of these hydrogens on this carbon. I'm just going to choose the guy on the bottom. And those two are going to come off. And when those two come off, that is going to make H2, which is hydrogen gas coming off, basically. The result of that is, again, absolutely nothing changes here. So just like everything else, you could draw it exactly the way it is. The only thing you should actually change is get rid of those two hydrogens like we did. So it's basically the only thing I got rid of. Now, what happens if we take, for example, a carbon-carbon double bond and we add hydrogen in that hydration reaction? That guy becomes a single bond and we add a hydrogen to each. Now, when we go backwards, if you think about it, and remove a hydrogen, that will put the double bond back on. And that's the exact same thing that happens here, where we lost the hydrogen, which always occurs between the carbon and the oxygen. We now need to make this a double bond to make sure we have the right number of bonds. And we end up with, as we talked about, we go from an alcohol to what is known as an aldehyde through this oxidation reaction. Any questions on that? Doesn't matter, again, if there's like 400 carbons attached there. You know, if you had a ton of carbons. Just to illustrate. And we're going to do our oxidation reaction. I am not concerned about anybody here except for this carbon, which again is my primary carbon. And I'm going to know in this oxidation reaction, hydrogen from the oxygen, hydrogen from the carbon. Those two again are going to come off in our H2 over here. And what should I do with the rest of this thing? I should draw it exactly the way it is, not change a thing, except for taking those two hydrogens off. So again, as I'm hoping you're seeing a pattern that you pretty much have the structure in front of you. You just need to make sure you adjust it accordingly and you'll be okay here. Count the number of carbons, make sure you don't draw enough of them there. Again, we took out the hydrogen, but we still have the oxygen. We took out one of the hydrogens, so that one's gone. Everything's the same. And just like we did above, we're now going to make the carbon-oxygen bond a double bond. And again, we end up with an aldehyde. So hopefully you can see again, even though this one's much longer than the first one, you end up the same. Yeah? And that's what happens when we oxidize a primary alcohol. Any questions on that? Now, what happens when we deal with a secondary alcohol in terms of a oxidation? Well, a secondary alcohol will look something like this. We'll do this. And I think this, and we'll do this. Okay. So starting here, this is again a secondary alcohol. And you may say, well, this got to be different, right? And the answer is no, it's not different. It's going to go through an oxidation, which means the only carbon you should be concerned with is this guy right here that has the OH group. And what are we going to do with this oxidation? We're going to do the same thing. We're going to take off an H from the oxygen and an H from the carbon. That again is going to give us our H2 that comes off, which basically is what makes it go through a oxidation reaction. And what about the rest of it? Everything's going to be exactly the same. We're going to draw it exactly element for element, except again, we're going to remove those two hydrogens. So we end up with something like this. And just like what we did in the previous one with a primary alcohol, we need to then finish it off by taking our carbon-oxygen bond and turning it into a double bond. We have now gone from a secondary alcohol to what is known as a ketone. The functional group of a ketone is carbon, carbon, carbon with a double bonded oxygen in the middle. That's the functional group, and that's what we got here. Again, doesn't matter if it is, you know, a ton of carbons involved. Doesn't really even matter if there's, you know, other things attached along the way. I'll just fill it in with some different stuff so not to draw the same stuff all the time here. And again, if this thing goes through an oxidation, all you should be concerned with is the carbon that has the OH group, which is this guy. And we're going to do the exact same thing that we've been doing. We're going to take off the hydrogen from the oxygen, hydrogen from the carbon, and then we're going to simply just sketch what's there exactly the way it was on the other side, except that we're going to remove those two hydrogens. I drew a whole bunch of other funky stuff in here. There we go. I think I missed the hydrogen there, by the way. So we'll put a BR there, hydrogen there, carbon, hydrogen. And again, here we're taking out the two hydrogens and we're going to leave the guy at the end. And we're now going to finish it by making that carbon-oxygen bond a double bond right there between the two. And again, we end up with our ketone. So the oxidation of a secondary alcohol results in a ketone. The oxidation of a primary alcohol ends up in an aldehyde. And by the way, the functional group for an aldehyde is this guy here. Question on those two. Well, we had a tertiary alcohol, so let's see what happens with that guy. So if I draw a tertiary alcohol like this, and we'll do this. That would not be a tertiary alcohol. Let me actually draw a correct one. Get rid of that right there. There we go. Okay, so tertiary alcohol right here, this carbon attached to three other carbons. Again, tertiary alcohol. This goes through an oxidation reaction. What do we need to do? We need to do the same thing we did on the other two. We need to go to the carbon, oxygen, remove an oxygen, hydrogen there. And from the carbon, we need to remove an hydrogen. Kind of problematic right here. If we look at that carbon where we normally take the second hydrogen from, there's no hydrogen there. Because that carbon does not have a hydrogen, because it's a tertiary alcohol, you get no reaction. It will not go through an oxidation reaction, because an oxidation reaction means removing, in this case, 2 hydrogens. Although we do have one, we're missing that second hydrogen off of that carbon, which means a tertiary alcohol will not go through an oxidation reaction. Any questions on that there? So primary alcohol goes through a oxidation reaction, remove the 2 hydrogens, one from the oxygen, one from the carbon, make a double bond between the carbon and oxygen, nothing else changes, produces your aldehyde. Secondary alcohol, also remove the hydrogen from the oxygen, hydrogen from the carbon that's attached to the oxygen, make a double bond, you end up with a ketone. Tertiary alcohol cannot go through this reaction because it's missing that critical second hydrogen on the carbon. Now, these are all oxidation reactions. What would be the reduction reactions? Well, oxidation reactions always goes with reduction reactions. And when we talk about reduction reactions, it's actually this reaction in the reverse. Going this way would be the reduction reaction. We add H. One H goes there, one H goes there, and we go backwards and get our primary alcohol. Same thing with our secondary reaction. If we go in the opposite direction, that is a reduction. Again, one hydrogen goes here. One hydrogen would go here. Obviously, the double bond would have to go to make room for it, and that would produce our secondary alcohol. So oxidation reaction takes a primary alcohol to an aldehyde. A reduction reaction will take it backwards from a aldehyde to a primary alcohol. An oxidation reaction of a secondary alcohol will produce a ketone. Reduction reaction will take it back, and obviously tertiary is not doing much other than looking like a tertiary alcohol. Any questions on those reactions?